A database is a place where one process writes encoded data and another process reads it. That sounds obvious. But hidden in that simple statement is a time dimension that most developers don't think carefully about. The process that reads the data might not be running the same version of the code as the process that wrote it. In fact, the process reading data today might be running code written 2 years from now because data in databases outlives the applications that created it. This is different from service-to-service communication, where both sides are usually running simultaneously. A database record written today might be read by code that doesn't exist yet. That's a forward compatibility requirement that extends indefinitely into the future. The practical consequence: when you perform a schema migration adding a new column to a table, for example, the database can update the schema metadata, but it typically doesn't rewrite the existing rows. In most databases, when you add a column with a default value, the old rows appear to have that value when read, but the storage bytes for those rows haven't changed. The database generates the default at read time. Now consider what happens during a rolling upgrade. Some nodes are running new code that understands the new schema. Others still run old code. A record written by new code, with the new field populated, gets read by old code. The old code must ignore the field it doesn't understand. It processes the record and writes it back. When it writes back, does it preserve the unknown field? The book is explicit about this. An application must be careful that it preserves unknown fields when rewriting data. If you read a full record and write it back, you must not silently drop fields your current schema doesn't know about. This is a subtle but serious correctness requirement, and it's violated more often than you'd expect. The encoding format you choose, and how well it handles unknown fields, determines whether your database migrations can be safe and gradual. REST is not a protocol. It's not a library. It's an architectural style, a set of constraints on how networked systems should behave. Roy Fielding described REST in his doctoral dissertation in 2000 as a generalization of the architectural principles that made the World Wide Web work. The web scaled to billions of pages and billions of users not because of any single technology, but because of its architecture: stateless servers, resources identified by URLs, uniform operations defined by HTTP methods, and hypermedia links that let clients discover what they can do next. REST applied to APIs means you model your system as resources, users, orders, payments, events, and expose them through URLs. Operations are expressed using standard HTTP methods: get to read, post to create, put or patch to update, delete to remove. The server is stateless. Each request contains all the information needed to process it. Responses include links to related resources, allowing clients to navigate without hard-coded URL patterns. REST APIs use JSON or XML for message bodies, human-readable, flexible, no schema required up front. That's both a strength and a limitation. Flexibility means fast iteration. No schema means documentation is the only contract, and documentation goes stale. The alternative that REST largely displaced in modern development is SOAP, Simple Object Access Protocol. SOAP is XML-based, heavyweight, and built around Web Services Description Language, WSDL, schemas. It was designed for enterprise integration and carries a lot of complexity for situations that don't need it. REST won not because it's technically superior in every dimension, but because it matches the mental model developers already have: the web. Understanding how a REST API works requires knowing HTTP. Almost every developer already knows HTTP. But REST has a limitation that becomes significant at scale: it's synchronous. The caller sends a request and waits for a response. If the response is slow, the caller is blocked. If the server fails, the caller gets an error. For high-throughput systems with many services, this tight coupling between availability and correctness creates real problems. Remote procedure calls, RPC, are as old as distributed computing. The idea sounds natural: make calling a function on a remote machine look exactly like calling a local function. The programmer writes ordinary function calls. The framework handles the network transparently. This idea has been implemented repeatedly, in different eras, with different names. Corebut in the 1980s. DCOM in the 1990s. Various Java RMI implementations. SOAP in the 2000s. And today, gRPC, Finagle, twerp. Every generation rediscovers RPC. But the book identifies why the transparent network call ideal is fundamentally flawed, not as an implementation problem, but as a conceptual problem. Local function calls and remote network calls are different in ways that matter and cannot be abstracted away. A local function call either completes or crashes. A network request can do a third thing: it can fail in the middle, with the caller having no idea whether the request was received and processed, partially processed, or not processed at all. If a post request to charge a customer times out, did the charge happen? Do you retry and risk charging twice? Or not retry and risk not charging at all? This is the idempotency problem, and it has no clean solution at the network layer. A local function call has predictable latency, nanoseconds to microseconds. A network request has highly variable latency, milliseconds to seconds on a good day, up to minutes when things go wrong. That variability makes it impossible to set timeouts that are both safe and fast. A local function can return any type. A network call must encode the return value into bytes, transmit them, and decode them, serialization and deserialization at every hop. Large objects can't be passed by reference. You can't share memory pointers across a network. The book quotes Jim Waldo's 1994 paper, "The fundamental difference between distributed and local computing has to do with failure, specifically with partial failure." Some parts of the system can be working while others are not. RPC frameworks that pretend this isn't true lead developers to write code that fails in subtle, hard-to-debug ways. Despite its flaws, RPC hasn't disappeared. It's been refined. And for specific use cases, particularly internal service-to-service communication within a company, modern RPC frameworks genuinely work well. gRPC is Google's RPC framework built on protocol buffers and HTTP/2. It uses protocol buffers for encoding, which means compact binary messages and schema-enforced contracts. HTTP/2 enables multiplexing multiple requests over a single connection and server-side streaming. gRPC is widely used inside Google and has been adopted broadly in the industry for internal microservices. Thrift powers Finagle, Twitter's internal RPC framework, and Facebook's internal service infrastructure. Twerp, built at Twitch, is a simpler RPC framework also built on protocol buffers. These tools accept that network calls are not local calls, and they provide explicit mechanisms for timeouts, retries, circuit breakers, and health checking. One key shift in modern RPC thinking: the service interface is now explicitly versioned. Protocol buffers schema evolution means you can add fields to requests and responses without breaking existing clients. Old clients send requests that new servers understand, and new servers return responses that old clients can read. The field tag discipline from Thrift and protocol buffers applies directly to RPC schema evolution. The book also notes an important practical reality: RPC is fundamentally tied to the request-response interaction model. The client sends a request, the server processes it, the client waits for the response. For many use cases, especially where the response isn't needed immediately, this is unnecessarily tight coupling. If a payment processing service is temporarily slow, should your order service wait? Should it fail? Or should it fire off the payment request and move on, letting the payment result arrive later? The answer to that question points toward a completely different communication model, and that's what the next section is about.